As I mentioned a couple minutes ago, there is actually a quantitative relationship between delta G and K, and we will derive it in a lecture or so. But for right now, I will just show you the equation, that delta G is equal to minus RT log K. This suggests then that I can go ahead and put in a value for K here and get a value of delta G out. Or put in a value of delta G here and find K. Well, let's go ahead and see what the kinds of values are that you would expect to see. And you see them down here right off. I've just done some of the math. There's K equal to 1,000. There's delta G equal to minus 17. There's K equal to 10 to the minus 5. There's delta G equal to plus 28. Two things are obvious that correspond to this particular functional relationship. One is that this is always a positive number, then this is going to be a negative number for the exponent. In this particular case here, this number is less than 1. That means that delta G is going to be a positive number. So there you go. K greater than 1, delta G negative. K less than 1, delta G positive. The other thing we see is the shrinking of the overall magnitude of the number. That log function there takes those exponents and it chops them down. It takes 10 to the minus 5 and throws away the 10 part in a log-based 10 function. So that's why we see the number 1,000 become a number like 17. The number 1 over 10,000 become a number like 28. So this mathematical expression suggests then that when you're looking at delta G numbers, you're going to see numbers which are positive and negative, yes, but they're going to have answers like 10 kilojoules and 20 kilojoules and 100 kilojoules and 1,000 kilojoules. That was for a combustion reaction. But when you're looking at K values, they're going to get exploded up to very large exponents. K's can be 10 to the 14, 10 to the 28th, 10 to the minus 56, all because that log function there is going to control the scaling substantially with respect to the magnitude of the number you're going to see. In general, then, when a reaction happens and goes great extent towards completion, delta G is going to be a big negative number, like 1,000 kilojoules for a combustion reaction. But K is going to be a gigantic, like 10 to the 70th for its exponent. Huge, huge number. Or if a reaction doesn't happen, that says that K is going to be a number that's less than 1, like maybe 10 to the minus 14, which means that delta G is going to be a small positive number. I want to quickly introduce you to an idea about a concept called stress. We're going to have an entire lecture on stress when we learn about this thing called Le Chatelier's principle. But stress is this ability to take a system which is at equilibrium and to perturb it, to mess with it, to make it change. You've seen me do this all the time when I've worked with students, where I would have a system up at the front that was at equilibrium, and one of the first things I would do would be to go get a blowtorch and run at the students with a blowtorch, and then they would all start moving around as I created the stress in the system. Or I'd go get some liquid nitrogen and pour it on the folks, and they would all slow down. These are external stresses on an internal system. And in fact, in understanding this idea about Q and K, you need to appreciate that when I look at a value like Q and I look at a value like K, what's always happening is that Q is trying to become K. But the thing is, once it becomes K, I can make it stop being K by driving it away using stress so that K becomes non-equilibrium and goes back to some new Q value. But then Q fights the stress and goes back and makes K. And then somebody stresses K and it moves away from Q to Q, and then Q turns around and comes back in the other direction. What are these ways I can stress a chemical system? Well, I just told you about one of them. I can use temperature. I can heat a system up or cool it down, and that can make the reaction move. That's why K values turn out to be temperature dependent. How else can I stress a system? I can stress a system because I put pressure on it. I've got a balloon, I set it down, I sit on top of it, I've increased the pressure on the system, and as a result, it drives it away from equilibrium toward some Q value, but then fights to get back to what K was. And a final way I can imagine doing this is if I decide to actually add material to the system, to change the concentration of the materials in there. That will stress the system away from equilibrium, and then it will drive itself back. So here's a really kind of clunky looking picture here to show you what I'm talking about. The important thing to see here is that there's this thing called the equilibrium constant equal to 2, the ratio of 2 to 1. Notice in this picture down here that it seems that on a bunch of different occasions, somehow I get to where the ratio of B to A is 2 to 1. There's my B, goes up to here, right about 2. There's my A, goes down to 1, 2 over 1, 2. A little while later, it's back to 2 to 1. A little while later, it's back to 2 to 1. Why is this? Because systems always tend to equilibrium. How can I make them go away from equilibrium? I can stress them. So for example, here I am at equilibrium. I'm going to dump a whole bunch of extra B into the system relative to A. The system says, I don't like that. It fights it, and it comes back to 2. Later, I dump a whole much more B than A into the system, A than B into the system. It goes away from equilibrium, it fights it, and it comes back to where I was before. So you see this kind of tension here, where Q can be greater than K, Q can be less than K, but always, over time, Q fights to get back to whatever the equilibrium constant is. This is stress in a system, and this is one of the things that we're going to study in more detail when we look at Le Chatelier principle in the next lecture.